if you are asked to either come up with the coordinates or find out, there's a bunch of these on the homework where you were given this big shape and then you're told you're going to rotate a segment or a triangle like 90 degrees clockwise about a point. Remember those on the 7-3 assignment, right? People are having trouble with that a little bit. And I can see why. It's kind of hard to visualize where they're going to go, but there's a foolproof way if you're going to do an increment of 90 degrees on a rotation. So, 90 counterclockwise, 90 clockwise, 180 either way, it's the same thing, right? If you're doing something like that, so let's make this, how about a 90 degree counterclockwise rotation. Pretend we don't see that where the red image is. We just start with the blue pre-image. And we want to find out where that stuff goes, right? Here's how you can do it. Break the directions to each vertex up separately into horizontal and vertical directions. Think of it like a roadmap for an ant to crawl from the origin out to point B. If the ant can only walk on the horizontal streets and the vertical streets, right? He can't cut through somebody's yard. He's got to just walk on the streets. How's he going to do that? He's going to go, how would we say this direction right there? That arrow I'm pointing at.
Right.
Describe that. Right by 4. Okay, so he's going 4 to the right and up 1. So do these for each vertex one at a time, and you're going to take each vertex and you're going to rotate each vertex from the pre-image to the image. And then when you're all done, you'll have the whole image there, but you treat them one at a time. Now, if I take each of those individual horizontal and vertical directions and I rotate them each 90 degrees counterclockwise, look what happens. If I take that guy and rotate it 90 degrees, about like that, and I'm going to start at the same spot, so he goes there. If I rotate it 90 degrees, wouldn't you agree that 90 degrees clockwise, if I start going left, 90 degrees clockwise rotates that arrow to up instead? So instead of right 4, we go up 4. Instead of up 1, what are we going to do if we rotate that arrow 90 degrees counterclockwise? It's going to become left, isn't it? We take this guy and rotate it 90 degrees, like so. And if I add those directions together, all that means is I'm just going to put those two arrows, what we say in math or in science, we call it tip to tail, right? We take vectors and we add them up like that. We always have to add them. Wherever one ends, the next one starts, right? Does that make sense? So if we take those two directions then, rotate them each individually, put them together, it doesn't matter the order either, does it? Doesn't matter. I could choose to go left 1 and then up 4. It doesn't make any difference. They end up at the same spot, right? Take the original two directions, rotate each one individually by whatever our rotation is, put them together, and it takes you to the image from the pre-image. Make sense? So instead of going right 4, up 1, that becomes up 4, left 1, right? How about this guy? What are the two directions associated with A? Assuming that we're going to rotate this about the origin, that's where the tap goes, and that's always where we measure the directions from, is the center of the rotation. So how would we describe those two directions? 2, what's that one?
Right, 2 down, 2.
Okay, yeah, 2 to the right, 2 down. Take each one of those and rotate them 90 degrees. Let's do the same thing. Let's go 90 degrees clockwise or counterclockwise. So the 2 to the right becomes 2 up. The 2 down becomes 2 left, right? 2 left, correct. Put those together, that's where we end up, right? Okay, so what used to be 2, negative 2, now becomes, the y value is 2 and the x value is 2, so 2, 2, right? Okay. That makes sense? That always works. Just break it into horizontal and vertical arrows, vectors, rotate the vectors, you got it. Now what if these had rotated the other way? That's okay. What if we wanted to rotate this, say 90 degrees clockwise, it's all right, just as easy. If I rotate a left arrow 90 degrees clockwise, where does it end up? Down. That guy becomes down. A down arrow 90 degrees clockwise ends up left. Yeah. Put them together. There's your new spot. Simple. All right. That's one thing I wanted to show you. Another thing I wanted to show you was this. Just a real quick question on this stuff. People were confusing. They weren't sure what we meant by coordinate notation, what we meant by vector notation, right? Component notation. So this is what we call coordinate notation because we're going to write both sets of coordinates, where we start and where we end, right? So what's this saying? Well, we're going to go from the point xy to the point x plus 4. What does that mean, adding 4 to x? 4 to the, if I'm adding 4 to the x coordinate, is that a horizontal or a vertical coordinate? Horizontal. So positive 4 in the horizontal direction would be to the right. So we're 4 to the right. Y is our vertical axis, so subtracting 2 from y means down 2. Makes sense? So we're going from coordinates x, y to coordinates, whatever x is, plus 4. Whatever y is, minus 2. Okay? How would I write that? So that's what we're doing. Now, how would I write this using component notation or vector notation? Right? That's the one where instead of writing 2 sets of parentheses, we're just going to write one vector. You could write it either way. It has to mean the same thing, though. It has to mean 4 to the right and 2 down. So how do I write that as a vector? Yeah, that's it. Just 4 in the x spot, because that's how much the x is we're being slid in the x direction. And negative 2 in the y spot, because that's how far we're being slid in the y direction, right? Make sense? Okay. A few questions on that I noticed on the homework. All right, so that's that stuff. Now, the only thing I just want to, I'm not going to do a lot with this. I'm going to let you kind of figure this out on your own a little bit here. But the last section is what happens when we do combinations of transformations together. Okay, so multiple transformations. Does the order in which 2 transformations are performed affect the final image? What do you think? So you vote. What do you think? Yeah, good, didn't it? Not always, but in most cases, it will. Okay, watch. Let's take an example. If we start with triangle ABC, the blue one right there, we can see what the coordinates are. There they're listed. Let's do 2 things. Let's reflect this triangle in the x-axis to get triangle A prime, B prime, C prime. So that's the first transformation we'll do. Now let's take that one and let's rotate it 90 degrees clockwise about the point 4, negative 5. So that's going to be the center, right? The center is, see, over 4 and down 5 would be like right there. If I go 90 degrees. And that's what we end up with. Okay? Does that make sense what we did there when we rotated? That's weird that we rotated it about some point other than the origin. But it's the same idea, isn't it? That stuff we just talked about, if we wanted to find out, just as one example, where B prime would end up, we're just going to rotate the directions to get there from the point of rotation, the center, right? So to get to B from the center, from point P, what would I do? To get to B prime, sorry. From there to there. How would you describe that in horizontal and vertical directions? Everybody see that okay? From P to B prime before we rotate. What is that? You had to describe, tell an ant how to get from P to B prime. What do you tell him to do? Up 3, yeah. So the only arrow we have is an up arrow pointing up 3. If I take an up arrow and I rotate it 90 degrees clockwise, what direction does it end up with? What do we end up with? Yeah, right. So the directions will be, instead of going up from the point P, because that's where the tack goes, instead of going up 3, we go right 3, and that's how we get V double prime. We can just do that for all 3 of them. We end up there. Okay, now let's see what happens. Let's compare that to what happens if we reverse the order of those two transformations. What if we rotate first and then reflect? So if we rotate first, it's a bigger rotation, isn't it? Now, why is it a bigger rotation? Why did it go so much further on the rotation, that one compared to that one? How come? How come that one's just a wimpy rotation? It didn't move very far. Okay, they're further from the center, aren't they? Right? The further you are from the center of rotation, the more you're going to rotate. Just like if you're on a merry-go-round, where's it harder to stand, on the outside or the inside? Outside. How come? Because you're going around, it takes the same amount of time to go through one circuit, but when you're on the outside, you cover a lot more distance, and so you're going a lot faster, right? So, okay, get the idea. So what if we rotate first, instead of going up, what is that, 7, we're going to go right 7, for example, to get to V prime. Now we're going to reflect that over the x-axis. That's a lot different, isn't it? Before, I think we ended up down here somewhere, right? So much, much different. Okay, definition. A glide reflection. A glide reflection is just what it says. What do you think it means to glide in geometry? Is that going to be translation, rotation, or reflection? Translation, yeah. We're going to combine a translation followed by a reflection. That's what we call a glide reflection. So it looks something like this. If I want to do a glide reflection to the blue pre-image, I'm going to slide it first, and then I'm going to do the reflection part. Okay? Make sense? Now, as long as you're gliding or translating the object in a direction that's parallel to the axis of reflection, it doesn't matter the order in which you do those two things. But otherwise, it does. So if you're doing a glide reflection, to be safe, what order should you always do them in? The order it says, right? It's a glide reflection. So you want to translate first and then reflect. In a few cases like this, it's not going to matter, but in most cases it will. Okay. I think we don't need to do this one. I think all this is showing us that the order changes, yeah, okay. If we do 2 or more transformations together, anything in math, if we combine stuff, we call it a composition, right? Because it's composed of more than one thing. So a composition of isometries or of transformations becomes that composition becomes its own thing. You know, it's 2 things put into one, but it's also going to be an isometry. That's the important thing. So because if I'm going to do a glide reflection, or if I'm going to rotate and reflect, or any combination of that stuff you want to, because each of those steps is producing from the pre-image to the image, they're always going to be congruent, the result will be too. All the measurements will be the same, so it's also an isometry. All right, I don't think there's anything else important for us to do. Just look at this one. No. I think we're okay. This is just, yeah, I'll put this PowerPoint up there. If you want to look at it, you can. This is just saying, once again, just reinforcing that if you do different order, you get different results. Okay, but that's about it. There's really nothing new here. It's just a definition of a glide reflection and sort of a combination, a summary of all the stuff we've learned. I think you're good to go. 7.5 is the last assignment. I'll put the review up also. All right, let's go to